So we're back on the bench with that PMC power supply we've been working on. There's a few things I want to do here today. I want to clean all the controls here, so the pots and switches, etc. And hopefully cleaning the amp or volt switch down here will clear up the intermittent issue with it. I want to take a closer look at this potentiometer here with the ball bearings in it, just because it's interesting, and with the front panel out we can get a closer look. Right now I'm going to go ahead and disconnect the transformer just from the main power switch here, just to make it kind of easier to move things around. I've drawn up a picture looking at the switch. So we have the switch body. Hopefully you can see the cap up here, and the color coding is red, black, and blue on the 3 wires. Capture that kind of stuff so you can put it back together. And we'll see if I can get lucky here and get these connectors to come off without breaking something. Of course, the black one's going to be stubborn. There it is. That'll make it a little easier to get into the front panel here. Give it a bit better inspection here. It looks good overall. The soldering I can see all looks good. I don't see any issues. Don't really expect anything major because it did work. Looking down on the edge connector for the PCB, the metal contacts down in there are nice and shiny and clean looking. There's no oxidization that I can see. Looking at the PCB, the connectors here are this whole board. Well, good chunks of this board have solder on them to beef up traces. But these look good and nice and clean here. There's no issues. There's no corrosion. You know, the tin plating and solder have kept the board clean. Again, that's really nice. But I am going to jump in here and figure out if I can actually get these potentiometers here are actually sealed, these wire wound ones. They feel nice and smooth. They don't bind. I don't really see a way to get deoxide in there, and those may be sealed enough they're not meant to be cleaned this way. Same's really true of the current limit pot here. It's not open to the air. It's got like a rubber sealing. It almost looks like it's rubber here. It's probably hard plastic. Sealing there. However, the switch here is open. And so we're going to shoot some deoxide in here and work this switch. You can see, hopefully you can see the metal tabs coming out of the switch have corroded. They've turned pretty dark and brown, so that the metal there has, you know, oxidized over the years, which is a good indication that what's inside of the switch is oxidized over the years. If I don't have a lot of luck cleaning this, I'll remove the switch and actually do a tear down and clean it internally. I've cleaned many switches like this over the years, just a tear down. I'm probably overdoing the cleaning here, but I seem to always do that. I can feel the switches become lubricated. It's not quite as stiff. The actions become really positive again. So I have some confidence that switch is back happier. Let me bring up the meter here. And get it in continuity. And we'll do some testing of the switch here. I'm going to get on the center pin there. on this. Oh, if I can get it to grip and stay. That seems nice and positive. It's actually an odd switch. It's not acting exactly the way I'd expect it to, but let's see if I can get in here, get some kind of contact down in there. It's going to be a bit of a challenge getting into the inside contacts in there. Maybe I can get in through the wires and get clipped on. I think that'll do it. Let's test the other side of it. Doesn't seem intermittent at all. However this switch is designed to work, it just seems kind of odd to me. It doesn't seem to be failing anymore to make contact, so I have some faith that the cleaning we just did has got that switch back to in operational state. That's really nice. Say the potentiometers are sealed, and I'm not going to find a crack and force deoxin in there. I just don't see that as a good thing to do. But while we have this apart, I'll try to get this in camera here. You can see the 3-ball bearings in the top of that potentiometer. Let me get it here where I can actually rotate the shaft. So there's 3-ball bearings, and the shaft from the knob is the little metal piece in the center of the 3-ball bearings. And as I turn the knob, you can see the ball bearings are rotated to one of the stops. And now with a lot of knob twisting, it'll rotate around to the other side, and it's taking a lot of knob twisting to get this thing around. We haven't hit the other stop yet. And even though it's a single turn there, it is a single turn potentiometer. This is producing a reduction gear set, so it's taking a bunch of turns of the little knob to get this to go through its 180 degrees or 270 or whatever it is of rotation. So those ball bearings really produce a reduction gear set in there. It's nice and smooth. It's a nice fitting little potentiometer. I'd be kind of afraid to get cleaner in here. There may be a bit of lubricant or something to provide additional friction so that it moves freely. It works well. I'm not going to do anything else with it, but it's an interesting potentiometer. Get back centered in camera. I've never seen one like this before. So I thought I'd share that. We kind of looked at it in an earlier video, but it wasn't a real good visualization of how it works. Next thing I'm going to do here is I'm going to prep a piece of wire. And with this, I'm going to tack this wire across the main filter cap. Actually, I may just catch it under the screws, and that'll bring out some leads so that I can measure the ripple across that cap while it's in operation easily. Getting on the circuit board here to places where I could actually hook a meter up is just really difficult. It's just not easy to do, and because I want to kind of look at ripple on that cap in operation under load, I thought we'd go ahead and do this. And the positive, get these little prepped. I should probably put some solder on these, but I'm going to be lazy. And at this point, I'm just going to catch it up under the screw. There's not going to be any current flow through these leads. Well, if I can get it to actually catch in there. There won't be any current flow through this. It's just for tapping off the voltage to look at ripple. So, a less than perfect connection and a temporary connection is fine. This is really just for testing the meter. That brings us out some flying leads so that we can look at it. While I have the board out, I'm going to reseat these LM723s. I believe they're op amps, but I could be wrong. Looking for the little screwdriver I was just using as a pointer here. The orientation of them is interesting. Pin 1 is here on this guy, and pin 1's over here. And even though they look nice and clean, I'm still going to just pop them about. Leads aren't bad. They're not super shiny, but they're not corroded. And this will just get it reseated in the socket. The socket relies on pressure between the pin and the socket pins to create an airtight contact without air getting in there. Without oxygen getting in there, it won't oxidize. And this just kind of refreshes that connection. Those are in there well. I don't see any signs of heat damage. And all these resistors, I mean, they're all looking almost new, if not new, a little dusty. This resistor here looks like it was bent over by somebody working on this power supply before. And I'm going to straighten it up a bit, and I straightened it up to add this air gap here in the middle to increase air circulation. Those are meant to dissipate some heat, and of course that's why they're near the caps, because you want heat on your capacitors. And yes, I'm being sarcastic. We've got heat coming off the heat sink, diode bridge, the pass transistors, and the resistors here, and the main caps just right on top of it. Physically, not a great layout. This thing is just convection cooled. There's a grill on the bottom of the case, which really is over here. I believe when it's assembled, actually no, the heat sink extends over here, so it's up underneath the heat sink to create some convection cooling, but it's not great. The layout is the layout. The other resistors look good. We know the supply worked, even under the load testing we did before. R23 here is in some sleeving, and it's also been bent over a little bit, and I'm just going to straighten it up here. I suspect somebody grabbed and bent it over, and that'll give me a bit of air gap between this capacitor and the resistor. I suspect the sleeving on here, that's actually a fuse. R23, that really looks like a fuse to me under that sleeving. No, it looks like an HRC fuse to me in there. I haven't actually spotted a fuse in this, so I wouldn't be surprised if that was a fuse. Yeah, and it's measuring down near 0 ohms, a tenth of an ohm or so. So that's actually a fuse. And I'm guessing the sleeving then is, if it did explode, help contain it. HRC fuse shouldn't necessarily explode, but so it's not a lot of heat up against this capacitor here. I don't know what brand these capacitors are. It almost looks like it says Frake something. Don't know. Don't recognize the name at all. I think we're at a spot where we can kind of set this all back together. Get to a point we can put a bit of power to it. Oh, no. It is unplugged. A few videos back you saw me make that mistake and have an interesting afternoon. So really, I think we can go ahead and kind of set piece parts in place. That cable runs up underneath there. What are you hanging up on? And I am going to put screws back in the back here just to keep things from flopping around. And of course, I didn't pay a lot of attention last week to what screws came from where, but that's obviously the correct screw. It's a machine screw and it was pre-threaded. So it just went on. That'll just kind of help hold things together. A little cleaner. Let's get the edge connector back on. And the thing that's going to be the most interesting to do, potentially because there's not a lot of working room, is getting these guys back on. It's kind of dark back in there. Makes it a little bit challenging. Let's see if I can move the wire tie back. Remember, we put the wire ties on to indicate which lead went where, and the wire ties are towards this edge over here. You can see that these leads are twisted as they should be. That just helps reduce noise in the end. These are an interesting little connector. And of course, the one with the wire tie again was closest over here. Those are actually pretty oxidized looking to me. They're not super clean. I may do a bit of a scrub on these. Just to help if there's any corrosion. They're just kind of dark looking. Ooh, that was way more deoxit than I needed. I always overdo it with the deoxit. End up with stuff that's wet. Okay, let's pull him back off, see if it makes it a little easier to get this one on. Wow, you just came off there, and you came off there very simple. There it goes. No, that's way too loose now. What have I done? Great. Trying to make things better, I've made things worse. There it is. Okay. Whatever little slot it's supposed to catch up in there, it finally caught in the right spot. And gave me a nice amount of friction getting on there. Our color coding was blue to the outside here, black to the center, and red for the power switch. That should sit back in place there, and it does. Those flying leads are trapped there. Get a screw here in the front panel, and I think those were self-tappers. No, it really wasn't, looking at it. Again, a nice indication of a little bit more build qualities. It's not just all self-tapping screws. See if I can kind of wrestle you around. Where I can get things to sit back in flush. And get the screw hole to line up. Oh, great. It didn't catch straight. Again, this is just to get enough pieces together that it's not flopping around and potentially shorting on something. I'm going to put the other screw in as well, just for some more stability on the front. Oops. Get the right screwdriver. 40 volts. And we'll just do a quick power output test just to see if it comes up and we have control still of it. So we are on DC volts, 40 amp range. There's potential here that big electric be put in is a bad cap, and it's going to either come apart, be shorted and take a diode bridge out, whatever. I probably should have tested it a little better before I put it together, but I didn't. We'll apply the mains. Although at this point we don't have, it's not on. I think I want to add a second meter in here. If I can find some leads to do it with. My little red and black slip-on alligator clips are missing. Got one red one captured up here, but I don't know where the two we were working with last weekend in the other video are. You know, obviously they're lost here on the bench someplace. If I got enough length with these. Hopefully I do. So we've got you on volts DC, your auto ranging. I just want to look at the gross voltage across the filter cap, and then we will switch over to AC volts to get a measurement of the ripple. I'm not happy with how that worked out. Let's twist those. You can see the little jumper lead I put in is red and brown. The red, of course, is the positive side. Well, if I can get that to catch in there. There you bet. See, hopefully we've got all of the meters in shot here. The voltage is all the way down. I'll just set the current clamp someplace centered. I've got the meter on volts. I'll pop on power quick and off. And I saw that jump to 39 volts. Okay, something's really unhappy. You probably heard the transformer hum really loudly there. So something's really unhappy. Something has drawn some current, and it's quite possibly that cap. Nope. Have I got the meter hooked up backwards here? Why was I seeing negative voltage there? Well, what have I got wrong here? Have we put something together incorrectly? We really haven't. Red, black, blue on the power switch. The orientation's correct. Oh, I see the issue. Really? Did I really do that? I sure did. Maybe you caught this earlier and or not. Sometimes, and this was something I was actually going to check as I thought through kind of the checklist in my head of things I wanted to look at on this, and I made a pretty fundamental mistake, I believe. We'll tear it back down and look. And as you know, in my channel, we share all the mistakes and stupid things I do. It's kind of why I'm here. Again, it's that lesson to those who are trying to come up in the hobby, or even those that are well experienced. We all make mistakes. It's okay. It's just kind of the reality of the hobby. release the edge connector if we can. See if we can fix this without unnecessary tear down. I think we can. Looking at the silk screen on the board, there's a nice little plus symbol down there for this cap, and the negative side of this cap is to this side. This capacitor is in backwards. And I suspect that's what's causing the high loading on potentially the output or the transformer. Just stupid. Let's see if I can rotate enough stuff here to be able to get at that. We are unplugged, and I confirmed it after I unplugged it. That capacitor is, I believe, right there. And we'll just love all the mechanical stress I'm adding to this cap by, I bent the leads over when I put it back in. Really sucks I put him in backwards. Not the first mistake I've made today, and probably won't be the last. Clean off the leads a bit here, make it a little easier to get it in. Straighten those out some more. So here in Seattle, over the last week, we had 2 really gorgeous days outside. Blue skies, sunshine. And then kind of the rain came back, but the rain hasn't been bad. But we just had 2 gorgeous days. Just 2 gorgeous days that, summers are kind of why I stay living here. I could work pretty much any place I wanted to. The black band is to the negative side this time. Yay. God. Sometimes, I even thought when I was kind of thinking this video through in my head about what we'd get done today, about check the orientation of the capacitors, and getting through all the things I wanted to do here, completely missed it. So I've got 1 lead tacked in. I didn't bend the leads over this time on the cap. Those leads were bent over to 8-inch soldering. The board was stuffed, flipped over, and soldered. This wasn't wave soldered, this was hand soldered. Almost guaranteed. So we didn't push it so hard we blew it up. And here's the perfectionist in me. The cap is not sitting flush, and I'd like it to sit flush. Hopefully the load that we had that caused the humming, and there to be no voltage output on the output, because that cap was essentially reversed biased and shorting. Hopefully that has been alleviated. I guess it would help to get the solder out of the way. I don't want to trap solder in here. Get this little back panel back in place, and we'll try again. I'm sure that cap is not too particularly happy with what I just did to it. Luckily I didn't run it for a very long extended period. It still wasn't good for it, what I just did. I've got to make a capacitor order, and this is I'll probably order fresh caps for this, even for the main filter. But for now my goal is just really to get it back operational and mechanically sound. don't see me using this supply a lot. There are places it could be useful. You know, if I need an additional rail beyond the 4 I can generate in my Rigol supplies. You know, 3 variable and 1 fixed 5 volt has a lot of versatility. But if I needed a 5th voltage, this might be a good little supply to do it with. I hope in this video or the next one we'll actually play around with the sense on the power supply and kind of demonstrate a little better what the sense is giving us electrically or electronically. Are you crimping a wire or something? No, there's not enough room there. It's just kind of stubborn. That would have been another obvious cause of why it was humming, was I had got a wire crimped and shorted. But in this case we didn't do that. I am seriously concerned about the surge voltage we're seeing here on the filter cap I chose. I definitely saw it go up above the 40 volt rating, and that is an experienced cap, which means we're really flirting with disaster. 40 volts. Current clamps in the middle, voltage is all the way down, meter set to volts, power switch is off. We'll hit power again for a second. No humming. It's a good thing. We're now seeing the about 35 working volts we saw before. This is a good sign. Let's bring the voltage up. That should be about 5 volts according to the meter movement, about 10 volts, about 15, and the top end at 20. So we're back to a functional power supply. So I'm going to set the output voltage to the maximum. Of course, there's no current draw here. I'm going to switch this meter over to volts AC and look at measuring ripple. And you know, a quarter volt of ripple, not even a quarter volt, that actually seems pretty small to me. But again, it's not under load, and that's a hefty cap, 2200 microfarads, so that really is in the noise. So now the question becomes getting some load on here and looking at a ripple. And we'll do the same exercise we did before with the electronic load. Of course, got to make room here because there's tools and stuff scattered everywhere. The caps we didn't use. The original load that we tried that just didn't draw enough current to really be useful. Got enough room here to work. Where did I put the load? Oh, there it is. Right in plain sight, as it always is. They've got this guy somewhat on camera. He's off. Bring the load resistance to the max. Rearrange the leads a bit here. And I need 2 more leads if I've got them floating around here. My Kelvin clips. Those aren't going to work. never have what you need laying close enough to be able to use it. That's just kind of a always reality. So let me stand up and get over to my sea of leads. So this guy, there should be a black one just like it floating in here. So we're measuring the output voltage. The load side. Oh, it really doesn't want to. There it is. Make good contact in there. So the load's hooked up. I'm not going to measure the current at this point. I'm just going to watch the output voltage. I can see the current on the meter, and by the way, the switch seemed to be working okay down there on the meter. We'll find out here. We're going to look at ripple on this filter cap. We're going to look at the output voltage, and we're going to provide a load on the power supply. So I've got the current at max, or the voltage at max. So actually I'm going to back that down to closer to 20. Rather than drive it as hard as it can be driven. You can see how fine a control I've got here. So there's 20 volts output, pretty spot on. Let's start to bring up the current here now. And you saw the voltage reacting. Switch the meter over to current mode. So that's someplace in the range of 400 milliamps. 500 milliamps. I'm actually wondering now if I'm actually able to measure the ripple here. Just watching the voltage dance here, why is the meter dancing around, the analog meter? We've seen it drop into compliance. Let's take the output voltage down. Something's not happy here. We'll get it to about 15 volts. It seems less stable than it was before to me. So 15 volts. No load. Current compliance as high as it'll go. 34 volts across the filter cap. Start to bring the load up. And that should be in the range of just over 300 milliamps according to the analog meter movement. About 600 milliamps. You're seeing the cap load down. But again, the 32 volts here is 12 volts above the 20 volt maximum on here. So even if there's ripple, even if there was a couple of volts of ripple on this 32 volt bus, the regulation would take care of cleaning most of that out and getting us a nice solid output. Again, that's just dancing all over the place. I don't trust that volts AC reading. Really don't trust that. I'm bringing up to 900 milliamps. Is that bad connection in the switch again? In AM mode, the meter movement's just dancing all over the place. Doesn't seem to be related to the switch. It's actually measuring or not, where before it was intermittent. This says we're drawn. Oops, just tweak the voltage. Get back up around that 15 we were working at. Good enough. It's about 700 milliamps, 900 milliamps. This makes me wonder if it's this pot over here, this cheap Chinese 10 turn. That looks pretty solid. Again, that's a worthless reading. You see in AC volts here, if the other meter actually does a better job of this. Crying little doggy downstairs wants to be up here with daddy. Oh, that didn't work well. Light on there and stay connected. Let's try a higher quality meter. Okay, that I believe, that you can't see that, but that's just at 0.6 volts of ripple. So this meter here isn't being happy about AC volts. And that I can actually believe. Because it's a constant current power supply, it's continuing to draw basically the 900 milliamps as I move the voltage around. And I'm seeing 0.6 volts, what I'm going to call ripple. So let's push this up. So that's 900 milliamps, and I'm seeing about 600 millivolts of ripple. And I'm going to bring the current down. I wish you could see this. As I bring the current down, the ripple is collapsing. So we're now down at 500 millivolts of ripple and about 700 milliamps draw. This is what I expected to see. I just don't have a way to get this meter in camera focus here. Maybe I'll try to swap these two meters around and see if this meter does a better job measuring the low volts AC. Amps. No. AC DC. There it is. AC amps. Amps, what am I saying? AC volts. We'll go to the 4-volt range. That's going to be AC volts. We want to measure across the filter cap. That's for measuring voltage. I don't want that ground shorting on something down in there. Power is off in the power supply. It was intentional while I move these leads around. So apologies for the phone call there. It happened right in the middle of the video. So we're back to trying to look at ripple current here. And we were looking at the filter cap. Let me power everything back up. And I'll try to pick up where we left off. Volts DC. Let's look at the output voltage on the power supply. Apologies for the noise in the background. We're outputting about 20 volts and we're drawing about 600 milliamps. I'm going to look at the ripple current here. So, you know, right now 391 millivolts or so of ripple current on the main filter cap, which is fine. The voltage on it is in that 30 volt range at the moment. We could actually go back to DC here, and we're over range. And take a look at the voltage, and there's 32.5 volts on him. Go back to AC, and we can look at the ripple current. But the next question here is, what's the ripple current on the output here? I'd expect it to be, you know, it's going to be much less. So let's figure out how to jumper things around here and measure that. I'll power off while I'm moving cables around. I don't want these to short any place. That wouldn't be good. See if I can get hooked up here someplace where we can measure the voltage, and we can actually grab onto it here on the electronic load. So this should let us measure the ripple current coming out of the regulated side of the power supply. And as you can see, it is very small. It is less than 1 millivolt. It's actually 0.3 millivolts. So you were able to see on the meter here the 300 or 400, whatever it was, millivolts ripple on the filter cap. And of course on the output it's nice and well regulated. It is a sensing supply, so it should work pretty well. I can bring the current up and see if we can increase the ripple. And you can see there's the power supply reacts to the increasing current load. So we're up, bringing up to about 900 milliamps. And the ripple comes down and it's very clean. Of course, I'm not looking at this with an oscilloscope. There's about 1 amp. And we're up around the max it can supply, about 1.2 amps, 20 volts. So the ripple, you know, based on an AC voltage measurement on the meter, looks really good. In this case, we'll actually go back and look. We can hopefully do this here somewhat safely. We'll take a look now at the ripple across the filter cap, and I would expect it to be significantly, well, not significantly, but I would expect it to be higher. So it's up over 400 millivolts. So no surprise there. The ripple on the filter cap, now that we're drawing twice the load, is nearly twice as big. It's about 740 millivolts. So again, what's happening here is the AC is rectified to fluctuating DC, and then that fluctuating DC gets into the filter cap. The filter cap's capturing the high point of that AC signal, and then has to send, you know, it absorbs the voltage there, and then has to send current back into the circuit as the voltage rolls off coming out of the diode bridge. And so the voltage ends up with ripples. I mean, literally ripples, because there's current demand on it. So, you know, just using a couple of meters here and looking, this power supply looks like it's working really well. I'm still a little concerned that I've got 35 volts or so across this 40 volt capacitor. It's pretty close to its working voltage. Oh gee, that's got to be distracting as hell. Washing machine is spinning. Apologies for that. Hopefully it's not too horrible there in the background. So pretty happy with this. Looks like a pretty good repair here. The supply seems reasonable. Seems to be holding its own. I am drawing the full 1.2 amps here at 20 volts. Voltage regulation looks really good. I should be able to maybe bring this back down to a flat 20 volts. See if we can get it up to exactly 20. As you can see, I've got really fine control here. I'm able to control this down to tenths of a volt on the output, which is really nice. I mean, that's a nice little supply. It's this gang pot where I've got the outer knob, which is gross voltage, and the inner knob here, which is fine voltage. Bring that down just a touch. And of course, I'm not going to be absolutely spot on 20. We're a little bit low now. Bring that up a tad. You know, that's showing a good solid 20 volts. I'll go ahead and take my higher precision bench meter here and figure out where I can poke leads in here, and I'll read the voltage on it as well. I don't know how well calibrated, and that's measuring actually 20.09 volts. Nothing says this meter here is spot on. Actually, the voltage rolled off there. That's interesting. Not sure why that happened. Maybe I bumped a pot here. But I'm pretty happy with it. For the $5 or $10 I paid for this power supply, it wasn't much. I don't remember now. It looks like a nice little supply. The fix was pretty easy because I happen to have a cap that would work in there. Oh, it's warm to the touch. The heatsink is warming up. I could potentially remove the transistors here and put fresh heatsink compound under them, but the heatsink actually feels warmer to the touch than the transistors do, which is good. So, you know, the heat is being drawn from the die, which is bound up or mounted on the bottom plate of the transistor. Heat's being pulled out into the heatsink. You know, I think at this point this kind of finishes up electronically what we're going to do with this power supply. Next thing we'll do in the next video is we'll look at the sense inputs and see if we can demonstrate a little cleaner voltage drop at high currents across leads. We'll use some of these cheap leads, so we'll get some decent voltage drop. And I think we'll be able to demonstrate that in the next video. I don't think I've got a whole lot else to say here. You have seen me waving hands around here a lot. And of course, I've got line voltage over here on the transformer taps, and I suspect this could be rewired for 240 or 120. There's enough taps on the transformer, and I waved my hand around here a lot, but I'm still several inches away from that transformer and from the lines voltage there. I'm very aware of it. It is a grounded chassis, which means this could be really bad getting my hand in there. But I have been cognizant of that the entire time. You probably saw me shock myself well several videos back. It's the same 5-fish electronic load that I think was in one of the first videos, or the first video I produced. It's useful for this kind of stuff. I mean, it's a constant current load, set around 1.2 amps. The heat from that's being dissipated through the old Pentium heat sinks here. Pretty nice. An expensive supply. Lucky fix for me with that cap. Don't know what the lifetime of this cap will be, the remainder of the working life on it. It is being worked a little bit hard. The 734 millivolts ripple is working the cap a bit. It's charging and discharging really 120 times a second. The 60 hertz converted to fluctuating DC was really being, like I say, charged and discharged 120 times a second. There's current being driven in, current being drawn out, in and out, and of course when there's current moving through resistance, it creates heat. There's current moving in the plates of the cap, which is producing some heat. I mean, it's not warm to the touch at all. I wouldn't expect it to be warm to the touch, but not really sure what else I can add here. I think I'll tear this thing down to get the test leads out and button the thing up, and we'll do another video looking at the sense connections for the regulation. So anyhow, I've said it like 3 times now. We'll wrap this up and we'll talk soon.